So far in this unit, we've learned how to simplify and perform operations with radical expressions. But in this lesson, we'll explore how to solve radical equations. So a radical equation is an equation in which a variable appears in a radicand. So here we have 4 examples of equations, all of them containing radical symbols. But which one of them is not a radical equation? And if we look at A, we see a variable as a part of the radicand. We see that in B as well. We see that in C in 2 different locations. So all 3 of those are radical equations. But letter D would not be a radical equation because the square root of 4 and the square root of 21, neither of those radicands contain a variable. So D is not a radical equation, but A, B, and C are. So let's look at how we would solve equations that would look like A, B, and C, where your variable is a part of that radicand. To do this, we have to understand the principle of squaring. What the principle of squaring says is that if A equals B, then A squared equals B squared. In other words, you can square both sides of an equal sign, and the equation will remain equivalent. So let's do our first example. We'll solve this equation. Let's first isolate that radical symbol. So our radical term, the square root of x, is actually equal to 4. And we can isolate the variable now. If we square the left side of the equation and the right side, we do this because the square root and squared are inverse operations. So they cancel each other out, which leaves me with just x as my radicand. So x equals 16. And let's double check that that's true. If I would plug 16 into this original equation for x and test out my solution, 4 plus 3 is equal to 7, so 7 equals 7. So this means that 16 is a solution to this radical equation. Now, one thing you must be careful about is that when using the principle of squaring to solve an equation, all possible solutions must be checked in the original equation. This step must be performed, and let's see why. If we solve this equation by first squaring both sides of the equation, what happens is the square root and the squared cancel each other out. So I'm left with 2x is equal to 25 because I'm squaring all of -5. So it's -5 times -5. And when I finish solving this, I get x is equal to 12.5, which appears to be my solution until I check my answer. If I check my answer and plug in 12.5 in for x, I get the square root of 25 is equal to -5. But we know that when simplifying the square root of 25 with that square root symbol, that's 5 equals -5, which is not true, which means that 12.5 cannot be a solution. So when we checked our answer, we found that that solution is actually not a solution, and therefore there is no solution. Now, if we think a bit deeper about this original equation, we'll see that it makes sense that there would be no solution. Because earlier in this unit, we learned that the square root of any number, when we're using this square root symbol, the radical symbol, is always going to be the principal square root. It has to be a positive number. But when you look on the other side of the equal sign, I have a negative number. So I should know that the square root of 2x could never equal -5. So it makes sense that there would be no solution. They won't always be that transparent, though. Let's solve 2 more equations. But before we do, let's look at a step-by-step approach of how to solve all radical equations. Step 1 is to always isolate your radical term. And then step 2, you use the principle of squaring, where you square both sides. In step 3, you'll solve the new equation once you've eliminated that square root symbol. And then step 4, the important step of checking all your solutions into the original equation. So let's perform these steps. I'll isolate my radical term in my first example to get the square root of 1 minus a is equal to 2. Now I'll square both sides. And when I do that, the square root and the squared cancel out, so I'm left with 1 minus a is equal to 4. I subtract 1 from each side. I'm just going to solve this new equation now. So negative a is equal to 3. And when I divide each side by negative 1, I'm left with a is equal to negative 3. So it appears that negative 3 is my solution. Let's check to make sure that that works. So 3 plus the square root of 1 minus negative 3 is equal to 5. So I get 3 plus the square root of 1 plus 3 is equal to 5. 3 plus the square root of 4 is equal to 5. The square root of 4 is 2, so 3 plus 2 is equal to 5, and I see that 5 equals 5. So that works, which means that negative 3 is my solution. It worked. And let's do one other equation. Now, in this equation, I have the square root, 3 times the square root of x equals the square root of x plus 32. And I actually have radicals on both sides. So where it says isolate the radical term as step number 1, I actually have 2 different radical terms that I can't combine, and I can't really do anything else with them. So in this step, I just have to keep them on opposite sides of the equation and jump straight to step 2. Let's use the principle of squaring since I can't isolate these any further. So I will square the left side and the right side of the equation. When I square 3 times the square root of x, I remember that the 3 gets squared, so that becomes 9. And the square root of x gets squared, so that just is x. And on the right side, the square root of x plus 32 squared is just x plus 32. Now I can finish solving my equation. I subtract x from both sides. So 8x is equal to 32. And divide by 8, so x should hopefully equal 4. Now let's test out that answer by checking it into our original problem. So 3 times the square root of 4 is equal to the square root of 4 plus 32. So this is the same thing as 3 times 2 is equal to the square root of 36, which is the same thing as 6 equals 6. So again, when I checked my answer, this one also worked. So that's my solution.